Apart from crystals and broken rocks, not much else in the cosmos naturally comes with sharp angles. While many objects have peculiar shapes, the list of round things is practically endless and ranges from simple soap bubbles to the entire observable universe. Spheres in nature are made by forces such as surface tension that want to make objects smaller in all directions. The surface tension of the liquid that makes soap bubble squeezes air in all directions. It will, within movements of being formed, enclose the volume of air using the least possible surface area. Using the freshman level calculus, you can show that the one and only shape that has the smallest surface area for an enclosed volume is a perfect sphere. In fact, billions of dollars could be saved annually on packaging materials if all shipping boxes and all packages of food in the supermarket were spheres. But practical matters prevail. Nobody wants to chase packaged food down the aisle after it rolls off the shelves. For the large cosmic objects, energy and gravity conspire to turn objects into spheres. Gravity is the force that serves to collapse matter in all directions, but gravity does not always win. Chemical bonds of solid objects are strong. The Himalayas grew against the force of Earth's gravity because of the resilience of crystal rock. But before you get excited about Earth's mighty mountains, you should know that Earth as a cosmic object is remarkably smooth. If you had a super duper jumbo gigantic finger and you dragged it across Earth's surface, Earth would feel as smooth as a cue ball. If a solid object has a low enough surface gravity, the chemical bonds in its rock will resist the force of their own weight. When this happens, almost any shape is possible. Two famous celestial non-spheres are Phobos and Deimos, the Idaho potato-shaped moons of Mars. On 13-mile-long Phobos, a person would weigh a merely 113 grams. Big and massive blobs of gas in the galaxy can coalesce to form near-perfect gaseous spheres called stars. But if a star finds itself orbiting too close to another object whose gravity is significant, the spherical shape can be distorted as its material gets stripped away. By too close, I mean too close to the object's Roche lobe, named for the mid-19th century mathematician Theodore Roche. The spiraling gas, after having passed from the giant across its Roche lobe, heats to extreme temperatures and is rendered aglow before descending out of sight into the black hole itself. We can understand the flatness of our galaxy by assuming the galaxy was once a big spherical, slowly rotating ball of collapsing gas. During the collapse, the ball spun faster and faster. The galaxy naturally flattened pole to pole, while the increasing centrifugal forces in the middle prevented the collapse at the midplane. This general flattening of objects that rotate is why Earth's pole-to-pole diameter is a tiny bit smaller than its diameter. At the equator, we use effect of centrifugal forces on matter to offer insight into the rotation rate of extreme cosmic objects such as pulsars, with some rotating upward of 1,000 revolutions per second. If they rotate, say 4,500 revolutions per second, they would reach the speed of light. To reach this density, you must compress all the empty space that atoms enjoy around their nucleus, creating a ball of neutrons with crazy high surface gravity. Under such conditions, a neutron star's mountain range needn't be any taller than the thickness of a sheet of paper. The largest and the most perfect of them all, the perfect sphere, is the whole observable universe. The universe beyond this spherical edge is thus rendered invisible and, as far as we know, unknowable. That's all for today. Thanks for watching. As always, subscribe, like, and don't forget to share.